Welcome everyone to Science Unwrapped. We're presenting tonight our grand finale of our 2025 Celebrate Undergraduate Research series because this is USU's Year of Undergraduate Research. I'm Professor Brynja Kohler and Chair of Science Unwrapped. On behalf of Utah State University's College of Arts and Sciences, we're really excited to have you here with us this evening. Now, we're very excited to welcome our featured speakers, undergraduate researcher Ethan Wayland and his faculty mentor, Dr. Reyhan Baktur. One minute, I got more to say. I have a big lengthy introduction. No, I gotta tell you how amazing these people are. Ethan is a senior electrical engineering major. He serves as student coordinator of USU's renowned Getaway Special Team, also known as the GAS team. This team was founded in 1976 when NASA started the Getaway Special program, which enabled students and other community groups to fly experiments in space on the agency's space shuttles. USU's GAS team flew more than 30 student-built experiments aboard 10 space shuttle missions and has contributed to Utah State University's famous distinction: USU has sent more student-built experiments into space than any other university in the world. I want to extend a special welcome to Jan Soika, who has been a long-term mentor of the program. Jan Soika. And if you've been on the GAS team, please stand up so we can also see you here in the audience. I've seen some alum. Yes. Terrific. All right, so the GAS team is currently working on an exciting satellite project Ethan and Reyhan will tell us about tonight. Ethan has served as student coordinator of the GAS team since spring of 2024. He's a native of Twin Bridges, Montana, and graduated from Twin Bridges High School in 2022. Ethan is the recipient of the USU Undergraduate Research and Creative Opportunities Grant, known as ERCO, which is a competitive grant that he's used to support his research. Following graduation from USU this coming spring, he plans to pursue graduate studies. Dr. Reyhan Baktur is an associate professor in USU's Department of Computer and Electrical Engineering. Her research interests include antennas and microwave engineering, and she is affiliated with the Center for Space Engineering at USU Space Dynamics Laboratory and collaborates with NASA Goddard Space Flight Center. A senior member of the Institute of Electrical and Electronics Engineers, Dr. Baktur is a recipient of that organization's Dudley Award for undergraduate teaching. She is active in the U.S. National Committee of the International Union of Radio Science and was the inaugural chair for Women in Radio Science. So let's welcome Ethan and Dr. Baktur to the stage. Thank you.
Well, thank you so much for coming this evening to join us. So let's get started. Everyone in Utah knows how beautiful of a night sky we have. Looking at the night sky, we always wonder what they are, right? We're always curious. So that's the same thing for human being all over the history. In ancient time, people thought maybe this is just some kind of deity holding up the heaven. And later on, people started to group the stars into different constellations and giving some shapes. For example, the Big Dipper, Big Dipper that you all know every night, and this one, Orion, the Hunter. So these days, the Orion comes at around 10:30 on east sky, but in about a month, you will see that much earlier. So I highly encourage you to go out and take a look at those string of 3 stars. They are beautiful. Now, just as doctors normally examine us by looking, by listening, and by reading the devices, in today's world, we study space through all of these space instruments. So from space probes such as Voyager 1, Voyager 2, now they are at the very edge of the solar system. That's the furthest man-made object, flying in space. 2 space telescopes such as Hubble telescope, James Webb telescope, and all of these, I think I will not point this because it so all of these satellites, and that includes the ones that built by Utah State University. So talking about satellites, I thought I will just point out, we like to study things by putting them into groups. So satellite, we group them as their size, large satellite, medium, small, and in the small satellite family, we have CubeSats, that's the one that Utah State built. And for example, like Starlink satellites that launched by SpaceX, those are mainly small satellites. So just to give you an idea. And this is an example I kind of like to use. So this train of satellites is called A train because it comes in the afternoon. So afternoon train, A train. And I like this example because it has an array of all kinds of satellites, from small to big. So maybe you can read about it on Wikipedia or have your parents read it with you, grandparents, so that will be a nice time. Now, I mentioned to you CubeSats. CubeSats is a type of small satellite, and they are special. And why they are special, those are the things that you will hear from Ethan later on. But when we talk about CubeSat, I want to point out these two. These two are NASA's CubeSat that flew by Mars. They are called Wall-E and Eva. So named after the movie, Wall-E and Eva. Now, I cannot bring you Wall-E and Eva, but I brought you a cousin of Wall-E and Eva. So this one is developed by Brazil and one of my colleagues, Dr. Swenson from our department, electrical engineering department. So this is a 6U satellite, exactly the same size as Wall-E and Eva, and I provided the antenna for it, which is hiding at the bottom. So that's my contribution, okay? And the USU has its own CubeSats. So I mentioned the Wall-E and Eva, so there's something I want to tell you about. If you have seen the movie, then you know this part. If you haven't seen the movie, please watch it. It's a really good movie. So in the movie, Wall-E asked Eva asked Wall-E, directive. What's your directive? And then Wall-E showed her that, hey, I am just cleaning up the Earth. So here, directive means what's your job? Okay, so directive means what's your job. Now, for us, for people who build satellite or in rocket, so directive, what's your job, has another name. It's called payload. So payload is what's your mission, what's your job. So you see a rocket over there. Let's say that's a Falcon rocket by SpaceX, and the Falcon is carrying So right here, it's carrying a spacecraft, looks like satellite. So that's let's say that's a Dragon spacecraft. Now, since the rocket is carrying the Dragon is the payload for the rocket. Now, inside the Dragon, there are things that is taken to International Space Station for the astronauts. So this is a resupply mission. So the payload is the resupply mission. So in Dragon, there are things for astronauts. And in addition, there are some boxes like this. So you see the boxes here? Those are called nanoracks, and we put CubeSats in it. So nanorack is also a payload. Now CubeSat goes into nanorack, right? So for nanorack, CubeSat is the payload. So finally, what is the payload? What is the mission or directive of the CubeSats? So this is the former CubeSat by Utah State University, and I think the developers are sitting here with you today too, so feel free to talk to them later, and Ethan will tell you about it. So for the previous satellite launched by Utah State, the directive or the payload is that white stick here coming out. That's called aero boom, and you will hear later today as well. So with that, we talked about We study space. We reach out for the stars by using space probes, by using satellites and telescopes. And we classify or we group satellites into large, medium, small, and CubeSats. CubeSats are type of small satellites. And Utah State University makes their own CubeSats. So with that, let's play a game before we continue.
All right. Yeah, so we're gonna do something a little more interactive tonight. Who's ever played a Kahoot before? Show of hands. All right, sick. We're gonna do that. So let me pull this up and let me get it started. And I'll give us a minute or two to scan in and join the game. It'll be super quick. It's just 5 questions. We'll just test general space knowledge. We'll quiz you on some of the stuff that Dr. Baktur talked about just now. All right, here we go. All right, first question. This one's true or false? All right. Is the moon a satellite, true or false? All right, that one's true. Good job. Most of us got it. That's good. All right, who's winning right now?
Whoa.
V's winning. That was immediate.
Okay, so you will get your prize after the presentation, okay? Mm-hmm. So Ethan prepared some treats for you. You will get that after.
All right, next question.
So which one is bigger? Is a TDRS satellite, which I put the description about, is that bigger, or is a Starlink satellite bigger? Which one is the larger satellite?
If you need a hint, it tells you the mass in the little blurb right here.
Yes.
If you remember how big a Starlink satellite is. All right, good stuff. Ooh, Sam is winning. Good job.
Good job.
All right, next question. What is Voyager 1? Is it a telescope or a deep space probe, a CubeSat, or a small sat? All right, good stuff. Most of us got that one. Good job. Sam is still winning. Good stuff. All right, 2 more questions.
Okay, which one is not NASA's mission statement? Which one is not NASA's mission statement? So 3 of them is yes, 1 is not, okay?
This one might be a bit trickier. Oh, most of us got it. Good job. Good stuff.
I got it wrong.
All right, Reagan's winning.
Reagan is winning.
All right, our final question. So this is a model of the sport satellite. What classification of satellite is this? Is it a large satellite, a medium satellite? Is it a CubeSat, or is it a pico satellite? CubeSat.
Good job.
All right. So our 3 winners here, I've got some cookies for us, but in the interest of time, I'll have you come up and grab it after we're finished here, and then we'll go from there. All right.
Oh, congratulations, Reagan.
Good job.
Good job.
Okay, perfect. So we got that out of the way. I wanted to talk about that because I wanted to kind of introduce. Dr. Baktur mentioned CubeSats a little bit. My name's Ethan. I'm on the GAS team. The GAS team has been a club at USU for a long time. We've been sending science experiments to space for a long time. Over the past few years, we've specifically been building CubeSats, which is just a type of small satellite, specifically in a cube shape right here. So I have a model of our last satellite that we sent up to space. This is our model of gas packs. This is actually how big the satellite was. So it was very small. It's only a 10-centimeter cube, but it works just like a regular satellite, and we were able to send it up to space and launch it and operate it and talk to it. So I wanted to talk tonight a little bit about the process kind of from start to finish of what it looks like to build a satellite. And I figured what better way to do that than to kind of run through start to finish what our process was for the gas packs, the last satellite that we sent up to space a few years ago. So I'll just talk a little bit about gas packs tonight. So gas packs is the Getaway Special Passive Attitude Control Satellite. Now, your first step whenever you're building a satellite is it needs to actually do something. It needs to actually serve a purpose, right? So we need to define a mission objective or directive, payload. These are all synonyms. You basically need to determine what is your satellite going to do? What's its function? And so there's lots of cool stuff you can do with satellites, interstellar science, earth science. You can do communications like the Starlink satellites. That's what they're for. But what we wanted to focus on is a technology demonstration. And what that means is we're basically taking some cool technology that could be utilized in space, but people like big $100 million NASA missions, they don't want to test, they don't want to put some untested technology on their satellite in case it doesn't work or in case it breaks. They don't want their mission to be dependent on that. And so a lot of university missions like ours will test this technology that hasn't been tested in space before, and then just get an idea if it works. Maybe it works, maybe it doesn't, and then we can report on that. And then maybe in the future, this technology can be used on larger missions in the future. And so the problem we were trying to solve with the technology that we put on our satellite is when the satellite comes out of the rocket, right, it's going to be rotating and just kind of spinning in whatever random direction. It's hard to control it, and if you've got like a camera or something, you're trying to take pictures of the Earth, it's really hard to make sure the camera is pointed at the Earth at any given moment because it's going to be rotating in a random direction, right? And there are ways that you can stabilize the satellite or control the rotation of it, but most of those take power, they take electricity, and that's very limited on a small satellite like this. So we wanted a way to try to stabilize the satellite without taking a lot of power, right? And so our solution to that is what we call the aero boom. I have an aero boom right here. It's a meter-long inflatable arm. It's kind of like a thick balloon is the kind of consistency it is. We put just a tiny bit of air inside of here, about 2 psi of air pressure, and then the idea is that's not a lot of air, right? And so you can tell this is flexible down here on the ground. I'm able to fold it up, and then the idea is I crumple it up and I stick it inside of this compartment on the satellite, and I close it up just like this. And then once the aero boom is out in space, that little tiny bit of air is a lot of air pressure relative to the vacuum of space, and so it's going to want to expand, it's going to want to pop out, and so I open the door, aero boom pops out, and then it's stuck out of the satellite like this. Here's a quick video of what it looks like to kind of have the aero boom deploy in a vacuum. This cylindrical chamber right here is our vacuum chamber. And so you can tell it kind of inflates like a balloon, and it's going to stay stiff and rigid just like that. And so here's how we're able to use the aero boom to stabilize the satellite is we're going to utilize drag. And so if you've ever been driving down the highway, right, and you're driving really fast, you roll down the window and you stick your arm out the window, what's going to happen to your arm? It's going to get pushed back, right? It's going to get pushed back by the air. And so we call that drag, is when you're traveling really fast in one direction and then the air is going to push you back in the other direction. And so the aero boom that pops out of the satellite is going to act just like an arm that's sticking out of a car window, right? It's going to catch the drag, and it's going to get forced back by that drag. And you're probably thinking, Ethan, there's not any air in space. It's outer space. There's no air up there. Actually, there is a tiny bit of air because GasPax was in a we call it a low Earth orbit. It was only about 400 kilometers above the surface of the Earth. It's at the very top of the upper atmosphere. And so there is a tiny bit of air up there still. And additionally, the satellite, in order to stay in orbit, has to be traveling very fast. Several miles per second is how fast the satellite's moving. And so, the faster you go, the higher the drag force is going to be. And so even though there's just a little bit of air, satellite is traveling fast enough, there is a little bit of drag, and we're able to utilize that. So that's what we're going to use to stabilize the satellite. How's that going to work? Well, let's say the satellite is traveling from the left of the screen to the right, and let's say it's rotating in some random direction. It's rotating clockwise, right? The air is going to catch the aero boom, and it's going to force it back to the left because the satellite's traveling to the right, right? So the arm is going to get pushed back to the left. It'll rotate around the other direction, and then it'll catch some drag on this side as well, the opposite side of the aero boom, and it'll get pushed back to the left on the other side, and then it'll keep going back and forth. The air pushes it to the left again, and then again, and then the idea is eventually it's going to reach an equilibrium point in the middle. And so as the satellite's traveling this direction, it's going to stabilize it in the direction that it's traveling. And so that was the idea behind gas packs. So all that to say, our first step when we're building a satellite is you need to pick out a mission objective. You need to pick out a payload. So the payload for the gas packs satellite was the aero boom. So the whole point of the satellite, we're just going to launch it up. We're going to deploy the aero boom. We're going to try to take some pictures of it, and we're going to verify that it actually stabilizes the satellite once it's in orbit. So step 2, I'll skip over this. This is the most boring step, is actually getting money to pay for your satellite. It's expensive to send stuff into space, and so we were fortunate enough to get a grant, a NASA grant called the CubeSat Launch Initiative. They paid for the cost of launch of the satellite, which is the biggest expense. Step 3 of building a satellite is actually designing the components, prototyping those, building those. This is by far the most intensive and longest step of actually getting stuff put together for the satellite. So show of hands, who has any ideas what physical pieces you actually need to like put in a satellite to make it function? Any ideas? Yeah. Yeah, you can totally use reaction wheels. That was the point of gas packs, is we were trying to, because reaction wheels take power. So but you can totally use stuff like that to orient the satellite around. Yeah, all the way in the back. It has an antenna, absolutely. Yeah, we're going to talk a lot more about antennas here in a second, but that's a very important part so we can actually communicate with the satellite. Yeah. You definitely need a power source of some kind. We use solar panels for our satellite. That's what most satellites use. Yeah. Any other ideas? Over there. Yeah. Yes, yeah, you do need to make sure your sensitive components are insulated or like protected from the heat, the extreme environment and stuff. It kind of depends. Yeah, right over there. A camera, definitely, yeah. We put a camera on gas packs so we could take a picture of the aero boom. All right, in the back there. A strong structure, definitely, yeah. We need to mount all of the pieces on, we used an aluminum frame for gas packs. It was anodized aluminum, and we need to make sure it's all stable and everything. So these are just a few components I could think of off the top of my head. We need batteries, we need solar panels, we need that structure to put everything together. We need an electrical board so all the components can talk to each other. We need a computer to actually run everything. We need to program that computer with some code. We need radios and antennas so we can talk to the satellite. We need to put our payload on the satellite, and then cameras and sensors, depending on what your mission is. So that's step 3. Step 4 is actually assembling the satellite. You run some final tests on it, and then what we call integrating the satellite is actually putting it in its launch vehicle. And so this image on the bottom in the middle there is a picture of gas packs inside of this rectangular box is called the NanoRacks CubeSat deployer. It's basically just a spring-loaded box. Once it's out in space, it'll just have the door open, and then it shoves the satellite out into space. That's how it gets into orbit. And so, we run all the tests on it, make sure everything's good, and then we put it in the CubeSat deployer. This red tag right here you can see on gas packs is the remove before launch tag. We just leave that on there until we're ready to actually launch it. We pull the tag off, and then that indicates to the satellite that it's ready to turn on the second it pops out of the deployer. I have the remove before launch tag for gas packs right here, which is super cool. This is the last, I guess you could say this is the last surviving piece of the satellite. The rest of it was sent up into space. Probably one of the coolest parts of making a satellite is the actual launch. Like I said, we got a NASA grant to pay for our launch, and so the way they did that is, they on the International Space Station, they need food and fuel and water for the astronauts every now and then, right? So they do these cargo resupply missions to the International Space Station, and so this one was cargo resupply mission 24. NASA contracted SpaceX to do the launch for them, and then NASA asked SpaceX, hey, is there any extra room on the rocket? Can we put this satellite on there? And that's how NASA was able to cover our launch for us, which is really nice. So GasPax was on the rocket there in that video. And then the final step of actually making a satellite is operating it. You need to actually communicate with it, make sure the payload is functioning properly, making sure everything's working there. There's a picture of GasPax on its way out of the International Space Station as it was deployed, out of the CubeSat deployer. And then there's a picture of our ground station and the antenna that we use to talk to the satellite. This is the first picture that we got from gas packs from the camera. You can't really see anything. There was no lights on gas packs. We didn't have enough power, and this was taken on the night side of Earth, so we couldn't really see anything. But one of the later pictures we got, this one looks a lot better. This was, it's a little tricky to see what's going on here. The camera lens was actually inside of the compartment that the aeroboom was put in. So if you can see my finger peeking through right here, that's where the camera lens was. And so the picture was kind of taken from the angle of right next to the base of where the aeroboom is. And so you can see this bit right here, this yellow bit and white bit, that's the aeroboom sticking out. And then this black part on the bottom, that is outer space. And then this white part on the top half of the image, this is the Earth. And you can kind of see some clouds and texture there, which is super cool. So it's very important that we communicate with our satellites and are actually able to talk to it and get some pictures down from it. And Dr. Baktur can talk a little bit more about that.
Thank you. Well, so Ethan told you that the previous satellite is at the low Earth orbit. It's about 400 kilometers from here. So that's about the distance from Logan to Cedar City, just in case you wonder. That's the distance. All right. Now, Ethan also told you why they want the satellite to stable down, not to tumble. So the idea is we want the satellite to be talking to us. So if I talk to you, it's better I look at you and talk to you. If I turn around and talk, you may not be able to hear me. So that's why we want the satellite to point to us. So that's one of the reasons that previously they had that aero boom. And earlier, some of you mentioned the reaction wheel. Yes, so those are all to make it not to move anymore. So I'm talking to you. I talk with my mouth, and you hear with your ears. And the satellite talks to us, or we talk to satellites through antennas, by using antennas. So here are some pictures of antennas, and I brought some of the antennas here. So the antennas can be just like this, a wire, like wire antenna. And it can be a patch, just like that, patch antenna, or horn. I got the horn, so horn antenna. So, and this one is a helical, very cool shape helical. So it can take all kinds of shapes. Now, one thing in common that you can see is they are mostly made of metal. As metal, we can see them, all right? Okay, so they are made of metal. And then we ask ourselves, what can we do better? For example, here, this is a wire antenna. And the last gas pack uses a wire antenna. So they work just great. They work just great, except for before you launch the satellite, the wire has to be tucked in. Once the satellite is in orbit, you will find a way to make it pop open. If the wire does not pop open, then we lose our satellite. So therefore, we thought, well, why don't we use a patch like this? So it can stay on the surface of the satellite, then we don't have to open it up. Now, earlier, one of you answered a really good question. You said the satellite needs a power source. So for a very small satellite like this, CubeSat, there is no any other power source other than solar panel. So sunlight is the only power source. And that's why you see the entire surface of this CubeSat is covered by solar panel, solar cells. Now, if I use a patch like this, put the patch in front of the solar cell, then I will basically sacrifice power. Our satellite will have less power. So I just brought a piece of paper. I put it at my face, and you cannot see my eyes. So what can you do to see my eyes and nose? Okay, now. You cannot see now. So, or at least not clearly. So what can you do to see my face clearly when I block it with a piece of paper? Yes? Try, that's a great answer. Yes, that's a great answer. Thank you. What else can we do? Yes? Move the paper, but if the paper has to stay there, what do you do? Okay, but yes, make it transparent, but how? How do you make it transparent? What else? Yes? That will be great. I'd love that. Okay, so there are many, many good answers, but one thing we could do is we can cut some holes on the paper, right? So those are all great answers. Those are all great answers, but as engineers, we normally go for the cheapest, best, fastest solution. We want to make things as cheap as possible, as fast as possible, and it will be as best as possible. So that's what engineers do. So therefore, in order to be able to see my face, well, we can just cut some holes on the paper. So here, we cut some holes on a piece of metal, make it into chicken wire. So we decided to go with that route, and here we go. So we could certainly buy some chicken wire and make those patches, or we have a very cool printer in our lab. So the students like Ethan, they use conductive ink. So that ink is made of conductors. They use conductive ink and print antennas in whatever shape they want onto glass. You said glass, yes, on glass, or on a piece of plastic, something that looks like plastic that you will hear later on too. So we print our chicken wire or print all those holes that another student holding there with an inkjet printer. So that's our solution for transparent antenna. So we make antenna transparent, but there's not so much trick to it. We just make antenna with chicken wire, and that's transparent. Now, next thing is, do we want antenna to be small or big? So big is great, I like big, but sometimes you can't really do something big. For example, our CubeSat is small, so you might need a small antenna. Or when it's small, you can hide it. You can hide the antenna on your contact lens, or sometimes we might need antenna in our body to help us see or help the doctors do diagnosis. So in those cases, we need a small antenna. And then when we want to hear something coming out from small antenna, if you have seen the movie A Big Friendly Giant, the girl asked the giant, hey, when I leave you, how would you hear me when I talk? And he said, don't worry, I have big ears, I can hear. So big ears allows you to hear better. So therefore, there are big antennas like that called big ears. Those are space telescope. They can hear things coming from space. So sometimes you say the universe is whispering, and those big ears can catch it. And then if you make many of those, if you make many big ears, so this is very large antenna. So if you make many big ears, then they can be used to get signals from something like Voyager 1 when it's flying by Neptune. So small antenna, great, so we can put it on something small like a CubeSat, but then we will need a big ear to listen to it, and that's what Utah State students do here. So they design small antennas to put on, small and transparent antenna to put on their satellite, and that is their payload. That is the new satellite's payload, new satellite's directive, okay? And then on the ground, they listen with a big ear here. So this is now on top of our building. Ethan's group just put it up there. It's a beautiful big dish antenna. So it can be small, it can be big. Both are very useful. All right, so now Ethan will tell you how he built the transparent antenna. You might want to put it closer to your house.
Yeah, so gas packs, I talked about gas packs earlier. Gas packs launched in 2022. Since then, the GAS team has been working on our next satellite, which is the Getaway Special Radio and Antenna Transparency Satellite. GASRATS. It's a pretty funny name, but basically, what GasPax was doing, it was a technology demonstration, and its payload was the aero boom. We were just testing that the aero boom was functional, right? We're going to do the same thing on GasRATS, but our payload for this satellite is going to be the transparent antenna. So the idea is we want to put our transparent antenna on the satellite. We want to be able to verify that the antenna works. We're able to use that side of the satellite for communication. We're able to send radio signals and also verify that light is able to get through it, and we're still getting power generation out of our solar panel right there. And so I'll just walk us quickly through what it looks like to design a transparent antenna. I do a lot of research with Dr. Baktur. In addition to working on the GAS team, my research is on how to design transparent antennas, because you're always trying to find the balance between maximizing your antenna performance and maximizing your transparency. There's usually a trade-off there. And so that's a lot of what I do. But your first step is you're always going to design it. You're going to simulate it, make sure it looks good there. And then you actually start building it. You get your materials put together. This picture on the right is some of our ink. And so we print our antennas. That way we're able to make them in whatever shape we want. The ink we use, it isn't like regular printer ink. It's like 3 parts water and 2 parts this silver, these tiny silver nanoparticles. And so it's basically just like silver soup, but that way we're able to actually make an antenna out of it, because your antenna has to be made out of something that is electrically conductive. And so that's why we use silver, because it's a conductive metal. And so we take that, we want the antenna to be as transparent as we can, but it has to be made out of silver. It has to be made out of a metal. We can't really do anything about that. The thing that we print it on, though, we have to make sure that that's also transparent. We print it on this material. I call it space saran wrap. It's kind of the texture and feel of saran wrap. It kind of feels like this, but it's not actually saran wrap. It's a material that's designed for use in solar sails. So here's a picture of a solar sail, and you can see that that's kind of translucent, and so we're just going to use that material. We print on that. That way we're able to let the light go through it. And so here's a picture of our printer, and then a picture of kind of what it looks like when we have an antenna that's fully finished and printed out. So you can tell it's printed on that transparent saran wrap material, and it's also printed in that kind of chicken wire sort of shape, where it's got a bunch of holes cut in it to let the light through. So your last step is you always want to test it, evaluate it, make sure your antenna works. A lot of the engineering prototyping process is a lot of revision and redesign as you look at your results, and so we end up doing a lot of that. But yeah.
Okay, so Ethan and his friends printed and built the antenna and put it together on a solar panel, and we were very happy. And then I took it for testing. When we tested, it's like our poor little GASRATS is running and running with all the sweat, but we couldn't quite hear it very well. So it's not talking loud enough for us. Well, and what do? So we can either just give up and go back to a traditional patch, or we just think about it. We work with transparent antennas, so that means it's clear. So how about we just clear our vision, clear our mind, and look for a solution? So with that, we need to get a good vision. So to get the good vision, we are very lucky, because at Utah State, Dr. Shen, she has a very cool scanning electron microscope. She operates a scanning electron microscope at physics department, and that microscope can allow you to look into eyes of a shrimp, and you can see all these compartments in nanoscales of this biological creature, or look at pollen. So we talked to her and asked her to help us to look at this printed chicken wire, that our transparent antenna, under the microscope. When we looked at it, so when you look at the print of the sheet, the print of the traces, they are beautiful, as you see, they are beautiful, very smooth. But when we looked at it under the microscope, because the ink prints because the ink prints one drop by one drop, they kind of stack up. They may or may not connect very well. So then that means the conductor is not so conductive. It has resistance. Okay, so think of this. So think when you have a big road, many cars are going, each car can go fast. But if the road is very narrow, then you have to get in line. So a bigger wire, thicker wire, will let electricity go easier. The smaller wire has more resistance. And when it has resistance, then the power we put into the antenna becomes the heat. So it becomes the loss, becomes the heat. So now that we know why our GASRATS antenna were getting tired and we couldn't hear it, is because our printed antenna is not as conductive. We know the reason now, so now we are working on how to print it even better. And then maybe we'll combine it with other material to make it even better. So we know what to do. We don't give up.
Yeah, so we're really excited. We're going to try to have GASRATS ready to launch by the end of next year, by the end of 2026, if all goes well. And so I'm really excited about it. I'll keep everyone updated on how the launch goes, but I'm really looking forward to that. Here's a couple pictures of the team on the launch pad for GasPack, so that's really exciting. But yeah, now that we diagnosed our problem with the antenna, I'm sure we'll have a functioning prototype here very soon, and then we'll be able to send it up to space and test it up there.
Great. So this evening we came here to talk to you about how Ethan and his team are working on the new satellite and antenna, and they are waiting to be launched. And meanwhile, I wanted to tell you about how we reach out for stars using all these space instruments. Now, that was my payload. That was my directive tonight. But now my real directive is I want to tell you, all of you sitting here are the real stars. So seeing you coming here to our talk just makes us very proud and happy. I hope you keep being curious and keep studying, and maybe very soon you will join us, and together we will design and create something really cool. Thank you so much.
Thanks, everyone.
I'd just like to thank Dr. Baktur for her contribution one more time. She has to go because she's driving all the way to Ogden, but Ethan will be here. So thank you very much, Dr.
Thank you. So Ethan will be here to answer all your questions. And if you have more questions, just send me an email. If you go to Electrical Engineering Department's website, you will see my picture. And if you have questions, send me an email. If you would like a tour of the lab, send me an email, and we can arrange that. So have a great evening, and thank you so much for coming.
Yep. The gas team also has a table out there, I think, so I'll probably hang out there after I'm done too, and we can talk more about satellites if we want to. So,
Questions?
yeah.
What kind of frequency bands do you guys use for transmission?
Yeah, so yes, yeah. So the question was, what kind of frequency radio transmissions do we use for communicating with our satellite? So GasPax, we used ultra high frequency, so about 470 megahertz was the band that we used there. On GasRATS, actually, since we've got we're going to have our transparent antenna, we're also going to have a backup antenna for our primary communications. So we're going to use the same frequency for our primary antenna, and then we're also going to use our S-band frequency for our transparent antenna. So the primary communications will be 470 megahertz-ish, and then the transparent antenna will be about 2,400 megahertz. So, yeah, up there in the back. Good stuff.
Ethan, very nice presentation. I was just curious if you can share more about your experience of when do you decide to build a simulation versus going for physical prototyping?
Yeah, it's pretty tough. We try to do our best to do both in as many scenarios as we can. We try to simulate first and then verify physically. In addition to that, like basically wherever possible, we try to actually do a physical test where it's feasible and where it's reasonable to do it. So, yeah.
So with your arrow boom,
Mm-hmm.
it can control pitch and yaw pretty well. So you think about roll? Oh, sorry. So your arrow boom, I can see how it could control pitch and yaw really well.
Mm-hmm.
Can it control like roll of the satellite even?
That's a good eye. It cannot control roll. So we could have the satellite. Let me put this in my pocket. We could have the satellite extended like this, but then it's still like rotating this way, right? Which is kind of an issue. So in order to compensate for that, we actually put what are called some hysteresis rods inside of the satellite, because we wanted to make sure the arrow boom stabilized it on all the other axes, and then just to make sure it wasn't spinning, hysteresis rods are it's like a ferromagnetic material, and it basically interacts with the Earth's magnetic field, and they resist changes in magnetic field. I'm actually doing some research on them right now. They're super confusing, and the math is tricky, but basically just because of entropy, they're gonna start to slow down the roll of the satellite in this orientation, which is super cool. So we use that as like a backup to the arrow boom. So really good question. Yeah.
Hi. are you at liberty to talk about some of the alternative ways you're trying to create the antennas? I mean, like, yeah, just go ahead.
Yeah, definitely. So chicken wire is like the simplest solution, right? And so right now, our problem that we had with this iteration of the design is just our silver material isn't as conductive as it needs to be, so it's too resistive. And so the solution to that would just be just buy some chicken wire sort of material and just like cut it into the shape that we want and put that on the satellite. That's currently our backup plan. So.
Okay, I was wondering things like like maybe annealing it, to reduce some of those gaps, or like an etch, like a mask and etch kind of situation.
Yeah, or like a screen printing sort of system. Those are all options that we're considering as additional backup plans if we need to. So
cool.
Yeah, appreciate the input.
Does the dimension of the holes is that a function of the frequency at all, or does it matter?
Not necessarily. Well, the answer is always like not really, but kind of. It's typically just the size of the outer edge is primarily what determines the frequency that it operates at. You want that to be about a half a wavelength of whatever frequency you're using. Typically changing the size of the holes that you cut in it are just going to have various effects on the impedance of the antenna. And so we build around that.
Okay, then will the satellite, because of the wind friction, I guess it has a terminus. It'll eventually fall back to Earth because of the drag.
Yeah. So GasPax launched. It launched in December of 2021. It was on the space station for a couple weeks, so it didn't actually get out into orbit until January of 2022. It was only in orbit for about 4 months, and then because it had so much drag from the aero boom, it actually deorbited after that time. So, and we expect GasRats to be up maybe a little bit longer because it doesn't have a drag-inducing device. Hopefully it'll be in orbit for about a year is kind of the rough ballpark for that. And when we launch it up, NASA makes us fill out this document. We do all the math to make sure it'll all completely burn up when it re-enters. It's not going to land in someone's backyard or anything. So it's all, GasPax is toast now. It doesn't exist anymore, unfortunately. Yeah.
We've got our next question back here.
Have you thought about using actual chicken wire?
Yeah, so that's our backup plan, like I said, is to use not like actual chicken wire. We'll use what's called electroformed mesh, which is, it's pretty much the same thing. It's just the dimensions are like very precise and accurate, and that way we can get it. And we know the exact properties of it. We know the exact conductivity. We know the thickness of the wire and everything. But pretty much we might end up using something like that. That's totally a possibility.
Do you think it might be practical to like attach an antenna directly to the aero boom? Because then it'd be really big.
You're not the first to suggest that. So this right here, this is we call this a helical antenna. And so, I mean, you could just like stick this inside the aero boom somehow, have it pop out, and then you're able to use this as an antenna. We like patch antennas. They're a good balance for what we're doing for our mission because they are basically strong enough in the direction that they're facing that we're able to get a good signal out of them. We're able to get a lot more data out of that type of antenna. But if we were to use a helical antenna like this, it has to be pointed exactly correctly at our ground station. Otherwise, we won't get a signal. So, but it is totally a possibility in the future if we wanted to do something like that. We would just have to make sure we have extremely accurate pointing capabilities of our satellite, which isn't something we're planning on doing for GasRats, but it's something we could do in the future for sure.
Perfect. We got our next question right back here.
Yes. What would be the feasibility of using different components on the satellite? Or I guess it's really two questions. Like the frame can act as an antenna, or maybe like the ITO conductive glass and the panels themselves, or the semiconductor material, or the interconnects. You could use those instead of a chicken wire. And also, how do like the electrical resistivity of the things like those various components, or the conductive ink, how do those actually affect the transmission or the RF handling of the the broadcasts.
Yeah. So your first question, it has been done before. Instead of like putting a transparent on top of an antenna, we could like use the solar panel as an antenna. That's something that can be done, where you like put your metal trace inside of like the PCB that the solar panel is built onto. That can happen. From what I understand, when you put it behind the solar cell, you lose a lot of your transmission, because that solar cell is actually going to block some of your signal when you do that. It's not something we've looked into super closely, but I don't remember the mission name off the top of my head, but there was a European Space Agency mission that did something like that, where they made their own custom solar panels, and they put the antennas behind the solar panels and then used it that way. So definitely can be done. There's also stuff like if people have like used the PCB of their solar panel and put some metal traces in there and designed it to act like a magnetorquer. So you put a current in there, and then that acts as an electromagnet, and then you're able to orient the satellite that way. So there's lots of possibilities there. Your second question for how the conductivity of it affects the transmission capabilities. Basically, the less conductive your material is, the more resistive it is, the more it acts like a resistor, right? And so if you put your current in, you put your signal in to something that's highly resistive, it means less of the energy is being transmitted as electromagnetic radiation, as your radio waves, and it means more of that energy is being converted into heat, which we don't want. So we want the ratio of EM waves to heat to be very high. And so that's why if our trace isn't as conductive, the material isn't as good as we want it to, that means more energy is going to heat instead of being transmitted, so our signal is weaker overall. So, good question.
Thanks, Ethan.
Mm-hmm.
I have a question about some of the graphs you were showing. I think it was during the testing phase before launch, that looked like beautiful flowers, and they were just sort of on a polar coordinate system or something.
Oh, yeah.
Can you tell us what those are telling you?
Was it this one?
Yeah.
Yeah. So this is a gain plot, and so this is basically measuring the relative strength of the antenna depending on what direction you're viewing the antenna from. So like if you're viewing, can you see my mouse? Yeah, if we're viewing the antenna from the front right here, we've got a very strong signal, as opposed to if I view it from like this side, my signal is a lot closer to the center of the circle. The further out it is, the stronger the signal is. And so this is just a polar graph right here. And so we can kind of visualize how strong the signal is in any particular direction. Yeah.
Has any of the design documents been published yet? I mean, I did a quick search and find an overview, but is there any juicy details, like what's the power output from the transmitter and his software-defined radio used and things like that?
Yeah, so as far as GASRATS, we haven't published a whole lot of stuff. We've published a couple of papers just kind of like in our initial research process trying to get the transparent antenna to work. But once we get the satellite launched and finished, we'll definitely write up a full report and we'll publish that, and that'll just be publicly accessible. It's not on our radar. It's not something that we feel right now is necessary to do. We are planning on, in a couple months, we're going to go up and we'll hike up the mountain and make sure we can communicate using our antenna with our ground station here on campus. And then hypothetically that should be good enough to make sure it functions, and we'll measure the signal strength and make sure it's good enough to scale up to the distance that it's going to be in orbit. So, good question.
Okay, so was any duct tape used in the construction of any of these satellites?
Not duct tape. Let me see if I can find the picture of gas packs up here. There was some tape. You see this orange bit right here? This is Kapton tape. It's like tape design. It's not like designed to like hold stuff together. You just use the tape when you're assembling stuff to kind of like hold it in place, and then you like screw it down. But yeah, there was tape on gas packs, it looks like. So.
Any other questions?
Yes, I do have another question. Was there anything on your previous missions that you learned about sending these satellites into orbit?
Yeah, I mean, there's a lot. I could go into a long list. We're trying to be better this mission about documenting all of our progress, documenting all of our research that we're doing. That's something big that we're trying to do better about in the future. There's also, I don't know if this is so much of a lesson learned, more of just like a thing that happened, but there was an electrical failure with some components that we bought for our electrical power system for gas packs, and so we only had like 2 out of our 5 solar panels functioning a couple weeks into the mission, which was a bummer. And so that's why it kind of piqued our interest, and that's why we kind of got into doing the transparent antenna stuff for this next mission. Is like, well, power generation is really important, and we want to maximize that. But also just being aware that stuff can happen, stuff can go wrong. Just building a bunch of contingency and have a bunch of backup plans. So that's kind of one of the big takeaways.
Beautiful. We got one last question right here.
Cool.
It's actually 2, but
all good.
One, so with your transparent antenna, you're using silver nanoparticles. So how are you, if you are dealing with any tarnishing issues that might arrive? And then the second question is, about how much gain does your ground station antenna actually have?
Yeah, so the antenna itself, if we were just to like print it and then put it on the satellite and then send it up into space, it would like immediately sublimate and just like evaporate and like turn into dust. And so we're actually going to coat it in this conformal coating material, and it basically we're just going to like spray it with it, and it's this transparent material. It's used for coating PCBs for space use, to just like make sure that they are like operating fine and their thermal characteristics are fine. But it'll basically create a vacuum seal and just seal the antenna in. That way it won't just like evaporate, because that wouldn't be any good. So we'll make sure we do that. And then remind me what your last question was.
About how much like decibel gain does your ground station?
Yeah, so our ground station here, I don't know if I know that number. CJ, do you know that off the top of your head? Okay. So we've got 2 different antennas on our ground station right now. Like I said, we've got 2 different frequencies. So we've got one antenna for each frequency. Yep. Yes, yeah. So the Yagi antenna, yeah, I don't remember off the top of my head. And then we have the parabolic dish. I think this one is upwards of 20 decibels, but don't quote me on that. 32 decibels. And then the Yagi Yuta antenna, that one I don't know off the top of my head, so I don't know if I could give you an accurate ballpark. But yeah, we can, let me look that up real quick, and then we can talk after, and I can find that number. So, good stuff.
And if the audience has more questions, please come forward. Ethan will stick around for a bit longer, but let's thank him once again for his work and his talk tonight.